Hello online viewers, welcome to our lecture video on the topic curves. In this lecture video, we'll be talking about curves, types of curves and different elements of simple circular curve. So firstly, in order to talk about curves, firstly we'll be talking about what is curve and why is curve required. So as you can see here in the figure, we have our alignment from IP0 to IP1 to IP2, IP3 and IP4. As you can see here, from when you move from IP0 to IP1 and IP2, in this section, as you can see here, over here our direction change. So we have our alignment going in this direction, and from this direction our alignment is changing in this direction. So as you can see here, when we have such an alignment for our highways, so when we have such an alignment for our highways comma railways, we cannot provide such an alignment because cars and rails cannot cannot move in such an alignment, cannot offer such a sharp turning. So in order to smooth our transition, so as you can see here, our main point is why curve is required. So in order to have smooth transition when there is a direction change, so in order to have a smooth transition for in order to have a smooth transition for direction change in order to have smooth transition for direction change, our curve is introduced in this portion. So as you can see here, again in this portion, when we are moving from IP1 to IP2, and when we are moving, we have again a sharp turning over here. So in order to avoid this sharp turning, we have provided a curve in this section. We have provided a curve over here and over here. While moving from IP3 to IP4 as well, there is a sharp turning. So in order to avoid this sharp turning for our highways and railway, we have provided our curves. So we have for our highways comma railways, so for our highways comma railways, in order to avoid those sharp turnings and in order to provide our smooth transition, we have introduced curves gets introduced. So is curve necessary for every transition? The answer is no. So if we have pipes, let's say we have our pipes comma or pipelines, so pipelines, and if we have such an alignment for our pipes or pipelines, in that case curves are not required. Curves are not required because we do not need any sort of smooth transition for our pipes and pipelines. We only need our smooth transition for our roads or railways. So after having a basic introduction to curves and why is curve required, next we'll be talking about the types of curve, and to see a little bit more about curves can be different types. It can be either circular, parabolic or spiral. And as I have already mentioned before, curve is provided in order to change direction of motion smoothly. So curve is provided in order to change the direction of motion smoothly for our highways or railways. Next we'll be talking about, and as you can see here, our curve is always tangential to straight direction. So as you can see here, our curve is always tangential to two straight direction at its end, which is our alignment. So our curve is always tangential to its so as you can see over here, our curve is always tangential to its alignment alignment at its end. So next we'll be talking about types of curves. So what are the different types of curves? So we have two types of curves. So curves, when we're talking about curves, we have two types of curves: horizontal curves, and next is our vertical curves. So when is horizontal curve introduced and when is our vertical curve introduced? So simply our horizontal curves are introduced in our horizontal plane. They are used for our horizontal plane, whereas our vertical curves are used in our vertical plane, or specifically we can say that vertical curves are introduced when there is change in gradient. When there are gradient changes, in such cases vertical curves are introduced. We'll be talking further more about this in a later part of the video. So firstly, let me give the types of horizontal curves. So among horizontal curves, we have four types. We have simple circular curve, simple circular curve. And next we have the second is compound curve. Third we have reverse curve, and our final type of horizontal curve is transition curve. And on our vertical curves we have valley curve and summit curve. Valley curve and summit curves. Valley curves and summit curves. So right now we'll be talking about simple circular curve, compound curve, reverse curve and transition curves step by step. So as I mentioned before, this is what our simple circular curves look like. So let me put on the topic simple circular. So let me put on the topic over here, simple circular curve. So now we'll be talking about simple circular curves. This is what our simple circular curve looks like. So as you can see here in the figure, we have our initial point IP0, IP1 and IP2, and while moving from IP0 to IP1 to IP2 we have a sharp change in direction, and in order to provide a smooth transition for our railway or highway, we have provided a curve, and as you can see here, this curve has a center O and a radius R. And this type of curve is called as simple circular curve. So how is our simple circular curve different from other types of curve? So basically what we have in our simple circular curve is, our simple circular curve is basically a single arc of a circle. It is basically a single arc of a circle. So let me so if I had to draw, so let me just draw a circle of radius R. So right now, for examples, we have this center R. This is our radius R. This is our radius R. So as you can see here, right now we are just taking this section. This particular section is just a certain section of our circle of radius R. This is a single arc of a circle. Let's say we have taken this this certain part of our circle and kept it over here. So this curve is nothing more than a simple part of a circle of a radius R, and having center O, and having center O. And it is also termed as, it can also be called as simple horizontal curve. We'll be talking more about different parts of simple circular curve and different elements of circular curve and relation between them in the later part of the video. So as I explained before, so right now this is our point T1. This point T1 or this point T2, both of these points they are known as our point of tangency. Because our curve is a tangent to the alignment at this point. T1 and T2, our simple circular curve is tangent at this point, or this alignment is tangent to our curve at this point. So simply to describe our simple circular curve, it has a center O and a radius R, and it is simply a part of a big circle. So we have a big circle of center O and radius R, and we have to just taken a smaller portion of it and kept over here. Next we have is compound curve. So how is compound curve different from simple circular curves? This is what our compound curve looks like. So we have our certain alignment from IP0, IP1, IP2 and IP3, as you can see here. While we are moving from IP0 to IP1, we have a change in direction, so we have introduced a certain curve over here. And while moving from IP1 to IP2 to IP3, we have again a change in direction. So in order to provide smooth transition, we have provided another curve over here. So how is compound curve different from simple circular curve? So let me describe now compound curve. So as you know from the meaning of compound means many or more than one. So a compound curve simply consists of two or more arcs of different circles with different radii. So they have different radius as well, of with different radii. So what does this mean? So as you can see over in our simple circular curve, we had a certain circle of center O and radius R, and we took a certain portion of it and kept it over here. But what happens over here is compound curve is like a simple circular curve, but it is it is more than one simple circular curve, or we can simply say compound curve is a combination of simple circular curve, in the sense that it has one circular curve of radius R1 and the center O1, and as soon as this simple circular curve ends over here, another simple circular curve of radius r2 and center o2 has begin over here. So what is compound curve is? Compound curve simply consists of two or more than two curves. So as you can see here, we have a certain curve over here from t1 to t2. We have a certain curve ongoing, but as soon as this first curve ends, as soon as this first curve has ended, so as you can see here, from this point to this one too, as soon as this curve has ended over here, another curve of radius r2 and center o2 has begin over from here. So in order to have a compound curve, what we have, in order to have a compound curve, two curve must be, both of these curve must be combined. Two curve must be combined, and both of these curve must have a common tangent point. And both of these curves must have a common tangent point. So as you can see here in the figure, we have two curves of radius r1 and another curve is of radius r2, and both of these have a common tangent point at t2. T2. And one more special feature of compound curve which separates it from reverse curve is we'll be talking about reverse curve soon, but one difference from all type of from reverse curve is compound curve. Let me write it as CC. Compound curve consists center in same side of common tangent point. It contains the center in same side of common tangent point. So as you can see here from the figure, we have our common tangent point. This is our common tangent point, CTP, common tangent point, and in the same direction of in the same side of a common tangent point, we have both the center O1 and O2. They lie in the same side of our common tangent point T2 and T2. So this is all about compound curve. It basically consists two or more different arcs of different circles with different radius. It is just like simple circular curve, but it contains many simple circular curve, and it has a common tangent point, and both the center of this and the center of both of these circle must lie in the same side of a common tangent point. And the center might be in this side or in other side or in any other side, but the center must lie on the same side of this common tangent point. Next we'll be talking about reverse curve. So now we'll be talking about reverse curve. So let me put on the topic reverse curve. So now I have added my picture of reverse curve. So this is what a reverse curve looks like. So as you can see here, reverse curve is quite similar to our compound curve as we talked before, but there is only one difference between reverse curve and center curve, and the difference between the reverse curve and compound curve is that reverse curve do not have the center in the same side of our common tangent point. So as you can see here, as if in our compound curve, just as we talked before, it also has two circles, two arcs of different circle. One has a center O1 and radius O1, while other has center O2 and radius O2. So it basically has two arcs of different circles, and they also have common tangent point T2, T2. But the difference between compound curve and reverse curve is, as I mentioned before. So let me show the figure of compound curve. So what happened in our compound curve was, both the center O1 and O2, it lied in the same side of our common tangent point. So both of these centers lied upward to our common tangent point. But as you can see here, for our common tangent point T2, the first center O1 lies upward of this common tangent point, while our second center O2 lies downward of common tangent point. And as you can see here, for our reverse curve, it has changed our alignment as well. So as you can see here, our alignment has moved in reverse direction as well. So as you can see here, in this, there is no any change in our alignment. For our compound curve, there is no any change in our alignment, but for our reverse curve, we have our change in alignment. So reverse curve is introduced when there is change in our alignment, or we can simply say reverse curve turns the alignment. It turns our alignment in reverse direction. Or what we can also simply say is our both of these arcs. Both of these arcs, they contain a common tangent point. Both of these arcs, they do contain a common tangent point. In our case, it is T2. It is T2, but the center of both of these arcs, O1 and O2, they do not lie in the same side, or they lie in the opposite side. They lie on the opposite side. So So by this common difference, we can distinguish our reverse curve and compound curve. So now we'll be finally talking about our transition curve. So now we'll be talking about transition curve. So before we talked about reverse curve, so right now we'll be talking about transition curve. What is transition curve? So right now, as you can see over here in the figure, I have drawn a certain alignment over here. I have drawn a certain alignment in this way, and as I have already mentioned before, curves are introduced when you need a smoother transition. So as you can see here in the figure, uh, here is a change of alignment, or here is a change of direction when we move from left to this portion. So in order to provide a smoother transition, we have introduced a certain curve of radius r and having center o, but whenever a vehicle or a railway moves in this direction, and when we reach our point of tendency t1, where our curve meets our alignment or meets the straight portion, as you can see here, as we have moved over from here, and as soon as we reach this point t1, a curve of radius r has begun. As you can see here, from this point a curve of radius r has begun, and as you can see here, because of this reason, we have moved a straight line, and as soon as we reach our point t1, a curve of radius r begins. So there is still no smooth transition. There is no smooth transition because there is a rapid change in our alignment. There is a curve of radius r beginning. Still there is no smooth transition. So in order to provide more smooth transition, what we do is, between our straight alignment and our main curve, we introduce our transition curve. So as you can see here, so let me draw my figure this way. We have our alignment. So as I mentioned before, if we directly introduce our main curve between our alignment and our main curve of radius r begins, then we do not have a smooth transition. There is our radius of r beginning, and still accidents might happen, and there is still no smooth transition. So what we simply do is, we shift our curve downward. We shift our main curve. This is our main curve of radius r. We shift our main curve downward, and what we do next is, we introduce other curves. In this way. These curves have smaller radius, they have varying radius. So it's our main curve. So in order to provide more smooth transition, what we have done is, we have shifted our main curve downward. And next what we'll be doing is, we'll introduce curve of varying radius. They might be r1, r2, r3, and finally r. So as you can see here, transition curve is nothing more. It is simply a curve of varying radius. They are the curve of varying radius introduced between our main curve and our alignment. This is our alignment. This is our main curve. So what we have simply done is, we have shifted our main curve downward, and in order to provide more smooth transition, in order to provide more smooth transition, we have simply shifted our main curve downward, and we have introduced curve of varying radius. So as you can see from this figure as well, we have our main curve over here. This is our, from this point to point, this is our main curve of radius r. Next we introduce smaller curves. We introduce many more curves of smaller radius, of smaller or varying radius. They can be of varying radius. We introduce many more curves of varying radius r1, r2, r3, r4. So in order to of r1, r2, r3, so we do not have a so that we do not have a direct radius of r being begun as soon as our curve begins. So as you can clearly get my example. Let me show it one more again over here. We shift our main curve downward, and in order to avoid a direct increase of radius r, in order to avoid a huge turning, we introduce smaller curves or smaller radius, and they will be of varying radius. While our main curve has fixed radius r, while our transition curve will be a combination of many smaller radius. They can be r1, r2, and finally up to r, in order to provide a more smooth transition. And our transition curve can be spiral or parabolic in nature. We have our angle of deflection and many other angles which we will learn in elements of simple circular curve. So right now after completing our transition curve, now we'll talk about elements of simple circular curve. So now we'll be talking about elements of simple circular curve. So let me put on the topic elements of simple circular curve. We'll be talking about various elements of simple circle curve, and this is really important in order to understand about curve, and we'll be explaining the various elements of simple circle curve with the help of our this figure. So we have drawn our simple circle curve of which has our center O. We have our two tangent points T1 and T2, and I is our point of intersection. We'll be talking about all of them step by step. So first and foremost, we'll be talking about our first element, which is our first element is back tangent. So what is back tangent? So in order to describe our back tangent is our is simply our so let me show here. So back tangent is simply our tangent T1I at the point of our commencement. So this point T1, as you can see here, our curve has begun from this portion. This is going to be our point of commencement. So our point of commencement simply means from the point where our curve has begun. Point of commencement. So point of commencement. So our so as you can see here, this point T1I. So let me mark this by black color. So we have our tangent T1I. So this point tangent T1I denoted by our black color. This one is our back tangent. So let me show back tangent. So back tangent is our point T1I is our T1I. So from our figure, as you can see here, this T1I is known our back tangent, and for our definition, it is simply our tangent. It is simply our tangent T1I at the point of the commencement, or at the point of the beginning of the curve. Tangent T1I at the beginning of the curve, or and this back tangent is perpendicular. It is perpendicular to the normal OT1. So we have our normal over here OT1, and our back tangent T1I is perpendicular, so the angle between them is 90 degree. So our back tangent is simply our tangent to the tangent at the point of beginning of our curve, which is T1. So next we'll be talking about our forward tangent. So our first point back tangent has been completed. Next we'll talk about our number 2. We have forward tangent. So back tangent and forward tangent is quite similar to back tangent. Once you have understood back tangent, forward tangent is simply our it is our another tangent point IT2. It is our another tangent point IT2, but this line is a tangent. But we have this tangent point at the end point of our curve. So we have our point T2. This is our point T2 is our end point of the curve. This is our end point of curve. So as you can see, our curve has begun from T1 and it has ended in T2. This is our end point of curve, and our simply the tangent our tangent T2I, which is denoted by our red line at the end point of our curve. This much red line denoted by our this much is our back tangent. This is our back tangent, while this was our this is our forward tangent. This is our forward tangent, while our this portion which we talked before, this is our back tangent. So why this is named as back and this is named as forward? So as you can see here, our alignment is moving in this direction. Our alignment is moving in this direction, and it is going in this direction. So this and this. So this is our forward. This is our forward direction. As you can see here, we have as we are moving in forward direction, IT2. This has been named as forward tangent. But if we move in this direction, IT1, this is backward. We are going backward while we are talking about a backward back tangent. So our back tangent, this T1I, is named as backward, in the sense our alignment it is in our opposite direction of our alignment, while our IT2 or T2I, this is moving in forward direction of our alignment. This is moving in our forward direction, and this is our alignment direction has changed from over here. Our alignment has moved in this direction. This is our forward direction, so we have named this as forward tangent. So the name backward and forward is not so much important, but I just explained why this is backward and this is our forward tangent. Next we'll be talking about our third point. So let me give a basic definition of our forward tangent. Our forward tangent is simply our tangent IT2, tangent IT1 or IT2 at the end of the curve. I have already explained this from the figure, at the end of the curve, which is T2. So simply our tangent IT2 at the end of the port, at the end point of the curve is known as our forward tangent. So our third point, what we have with our third element of our simple circular curve is our third element is angle of intersection. Angle of intersection. So what is angle of intersection? So we'll explain this by our figure. Our angle of intersection is simply our angle between angle between our back tangent and our forward tangent. So we have our back tangent, which is our T1I, and we have our forward tangent IT2. The angle between both of these tangles, the angle between this forward and backward tangent, is simply our angle of intersection. So we have our back tangent T1I and our forward tangent IT2. So angle between both of them, between our forward and backward tangent, this angle theta is known as our angle of intersection. So known as our angle of intersection. So next we'll be talking about our after angle of intersection, we'll be talking about our, in fourth number we have our angle of deflection. So for our angle of deflection, our definition of our angle of deflection is simply it is our angle through which forward tangent deflects. So let me give you a little bit simple definition of what does deflection mean. So we have our certain alignment. Our alignment is moving in this direction, but from this point, so let me name this as point A, and from this point B, what we have is our alignment has changed the direction and is moving in downward. So our alignment needs to be moving in this direction, but our alignment has moved in this in a BC direction. So this change, this deflection, or this, as you can see here, this change in alignment is known as deflection, and this angle by how much it has changed is known as our angle of deflection. So let me show that in our curve as well. So this was our initial alignment T1I. Our alignment is moving in this direction, but from this point I we have a change. We have our change in direction of our alignment. Our alignment needed to move in this direction, but we got a simple change. We got a simple deflection in that direction of our alignment. So simply this one. So then simply this deflection. Let me denote it by del. This is known as our angle of deflection. So as per our definition, we said it is the angle by which our forward tangent turns. So with the reference of this line, so this is our forward tangent, by how much it has turned, by an amount of delta. This amount delta is known as our angle of deflection. So right now our angle of deflection is in the right direction. So as you can see here, our alignment was in this direction. So since now we have moved in right direction. So right now our angle of deflection is in the right direction, but our angle of deflection can be in left direction as well when our alignment is in opposite direction. So now we have our other element of simple circular curve, which is our in number 5. We'll be talking about our point of intersection. So point of intersection. So what is point of intersection? Point of intersection is simply simply the point where our back tangent and forward tangent meet. It is simply to give a simple definition, it is our point where our back tangent and our forward tangent meet. Back tangent and forward, it is simply the point where our back tangent and forward tangent meet. So in order to show it in our figure, so as you can see over here, we have our back tangent here, forward tangent here, and our back tangent and forward tangent have met in this point I. So this point I is our point of intersection. So this point I, point of intersection. So simply our point I is our point of intersection. So next we'll be talking about our point of commencement and point of tangency. So let me write in our sixth point of commencement, and now number 7 point we have our point of tangency. Point of commencement or point of tangency. So we can describe point of commencement as the point where our curve originates from the back tangent. So it is our point where curve originates, or our point of tendency is our point where our curve ends, point our curve ends, or simply we can give another definition as well. So our point of commencement is our point T2 and our point of tendency is our point T2. So I have already explained it in the earlier. So this is our point of tendency, or simply it is the point where our forward where our so our point of commencement is simply the point where our back tangent meets the curve, or our point of tendency is simply the point where our forward tangent meets the curve. So we can see it in this way as well. But in order to get a clearer example, a clearer understanding, our point of commencement in our name we have commencement, so it is our point where our main curve started, and our point of tendency is the point where our main curve ends. So next we'll be talking about our, in number 8 we have our we have deflection angle to any point of the curve. Deflection angle to any point of curve, in number 4 we talked about angle of deflection, which was this, but right now we are talking about other we are talking about deflection angle to any point of curve. It is different from our angle of deflection. So what is our deflection angle is? Our deflection angle is our, so let me write the definition first. So let me write it by deflection angle to any point of curve. This is our angle between back tangent and the chord joining point of commencement to that point on curve. So in order to explain this more clearly, so let me draw it in this way. So this is our back tangent. So in my definition, what did I told is our deflection angle is our angle between back tangent. This is my back tangent and chord joining point of commencement to that point of curve. So deflection angle to any point. So if I had to find deflection angle of any point, so let's say if I had to find deflection angle of this point A, deflection angle of this point, what I'll be simply doing is I will from my point of commencement I will join these 2 points. I'll join this point over here and this angle with the back tangent. Let me denote this angle by del. This angle is known as the this angle del will be known as the deflection angle will be known as the deflection angle to point A. So if I had to find the deflection angle of point A, I'll be simply joining the point and point of commencement and the angle made by this chord, this chord joining that point and joining the point of commencement with our back tangent, which is denoted by our del, is simply our deflection angle. Hope you have understood the term deflection angle. If you have one and if you have still any queries, we can comment down below. Now in our number 9 part, we have our tangent distance. So in number 9 we will be talking about tangent distance. So our so previously we talked about our forward tangent and backward tangent. The distance of both these points is simply known as our tangent distance. So we have our forward tangent as IT2 and we have our backward tangent at T1I. The distance of both these points or the magnitude of these lines is simply our tangent distance. So the distance of this line and distance of this line from T1 to I and T2 to I, the distance between our point of intersection and our point of commencement, or simply our distance between our point of intersection and our point of tangency. This is known as our tangent distance, and both of these tangent distance will be equal to each other. So the distance t1i and it2 are equal to each other. So let me write over here t1i equals to it2, and this is known, and this is our simply our tangent distance. So in number 10 we have length of curve. So what is length of curve? So our length of curve, let me describe it from my figure, it will be more clear. Our length of curve is simply our this length of the curve from our point of commencement to our point of tangency, from the length of this curve from our point of commencement t1 to point of commencement t2. So simply if I show it in this way, from here to here, this distance, this not the straight distance but this angular distance, this is known as our length of the curve. This is our length of the curve. So now in number 11 number we have our, now in number 11 we'll be talking about our long chord. So what is our long chord? So our long chord is simply our chord joining our point of commencement and point of tangency. So this point, so let me draw it by our black, this point. So let me first write down the definition. Long chord is simply our chord. It is simply our chord joining point of commencement and point of tangency. So as you can see here, this line from t1 to t2, this one is known as our long chord. This is simply our long chord. Next, in number 12 we'll be talking about mid ordinate. So what is mid ordinate? Mid ordinate is, so let me firstly write down the definition. Mid ordinate is simply our ordinate joining midpoint of long chord and midpoint of curve. So as you can see from the definition, so let me show it from the figure. What I wrote for mid ordinate is our ordinate joining midpoint of long chord. So this is our midpoint of long chord and midpoint of our curve. So what is our midpoint of curve? This is our midpoint of curve. So if we joined both of these lines, so if we joined our midpoint of long chord and midpoint of our curve, we get this point, we get this line denoted by our red line. So this is known as our this simply will be our mid ordinate. So now our last two remaining elements of simple circular curve are normal chord and soft chord. So we have already talked about long chord and mid coordinate. So after long chord we'll be talking about normal chord and soft chord and what are they. So I'm explaining those with the help of our figure. So as you can see here, we have a long chord over here. So let me draw this figure in this way. This way. So this is my length of the curve and this is my total long chord. So this is my point t1, this is my point t2, this is my long chord. The distance from t1 to t2 is our long chord, as I explained before. And let's say the distance from t1 to t2, this distance from t1 to t2 is 44 meter. So let's say the distance is 44 meter, and if I have to make equal division of this 44 meter, what I can simply do is I can make 10 equal divisions. So 10 into 4, which is our 40 meter. So I get remaining 4 meters. 4 meter is remaining. So from this point to this point, so let's say I'm going to make 10 equal divisions of 40 meter. So this 10 equal divisions of 40 meter is going to be our normal chord. So I divided my normal chord by NC. So now I have my remaining 4 meter. So what can I do of 4 meter is I can divide my 4 meter in 2 meter plus 2 meter. I can do that, or I can do 1 meter plus 3 meter. 1 meter at the front, 1 meter at the beginning, or 2 meter at the front, 2 meter at the end. Or what I can do is I can simply do 3 meter plus 1 meter as well, or I can even do 1.5 plus 2.5 meter. There are many possibilities. So the remaining distance of 4 meter can be divided in this way, and this division is known our soft chord. And soft chord occurs at our beginning and at the end of our chord, and at the beginning and at the end of our chord. So this is where our soft chord occurs, and our soft chords are always shorter than are always shorter than our normal chords. So hope you have got the idea of soft chords and normal chords. So this is where our soft chord occurs, and soft chords they can be of equal length, or they might not be of equal length, but our normal chords are always of equal length. So let me give our definition of normal chord and soft chord. So what is our normal chord means? Normal chords means our chord between two successive regular picks. So chords between two successive regular picks on the cuff, two successive regular picks, while our soft chords are generally shorter. They are shorter than normal chord, and they generally occur at the beginning and at the end of the cuff. They occur at the beginning and end of the chord. So hope you have understood about normal chord and soft chord. So as you can simply see here, this is our long chord. We are going to divide our long chord into number of equal divisions. So number of equal divisions in the middle, those are going to be our normal chord, and the remaining length can be divided in unequal divisions or in any sort of divisions at the beginning and at the end of the chord. Those unequal divisions, unequal or equal divisions shorter than normal chord at the beginning and at the end of the chord is known as our soft chord. Next we'll be learning about different relation between all these elements of simple circular chord. So we talked about 14 elements of simple circular chord. Next we'll be talking about relation between a few of them. So now we are going to learn about different properties of simple circular chord. So let me write down as different properties or relations. Let's use the word relations for now. Relations between different elements of simple circular chord. Different elements, or we can say this as properties as well. Different elements of simple circular chord. So yes, this is our simple circular chord. So right now I have another simple circular chord over here, and I'm going to list down the properties or those relations one by one. So firstly, I'm going to show my angle of deflection over. This is my angle of deflection. So this is my angle of deflection del, and this angle of deflection is going to be the angle, this angle T1 over T2. This angle is also going to be equal to del. So this is my first property of simple circular chord, which simply says that angle, which simply says our first relation is our angle T1 over T2 is equal to our angle of deflection, which is equal to our delta. So this relation is derived from our some basic properties of our circle, and it's a tangent. So this angle del will be simply equal to our angle subtended by our curve at the center. So both of these angles will be equal. Next we'll be talking about our second property, which is our angle subtended. So first let me write down the property, which is angle subtended by any chord, angle subtended by any chord at center of circle. Any center of circle is two times angle between chord and tangent. So what does this mean? So let me write this down over here. So what does this mean is, so in order to show what does this mean, so first line says angle subtended by any chord at center of the circle. This is our center of the circle. So let me draw any chord. So let me so right now I am drawing a chord over here from, let's say, this point to the center. Angle subtended by chord, we are going to name this angle as theta. So this is our first point. Angle subtended by any chord at the center of the circle is twice the angle between chord and the tangent. So this is my chord, and so let me join the line T1 and T2 over here firstly. So this is my this is my chord at the center of the circle, and next I need a line. So what is next is 2 times the angle between chord, this is my chord, and tangent. So this is my tangent and this is my chord. So let me find out the angle between both of them. So let me draw another line in this way. So this is my chord, this is my tangent. So let me mark this angle as del. So what is my so right now what is my second property tells me as angle subtended by any chord at the center of the circle, which is theta equals to 2 times the angle between chord and the tangent, which is del. So simply del equals to, so simply theta equals to 2 delta. So from our figure, angle subtended by any chord, we have our any chord at the center of the circle, angle subtended is theta, and this theta is simply equal to 2 times the angle between that chord and the tangent, the forward tangent, forward or backward tangent, whichever is closer, for or backward tangent which is any closer. So simply our theta equals to 2 del. So this is our first property. Next we'll so this is our second property. Now we'll be talking about our third property. Our third property states that angle subtended by a chord, angle subtended by a chord at any point on the any point on circumference, angle subtended by a chord at any point of circumference is equal to the angle between the chord and the tangent. So let me explain this with the help of our figure. So let me draw this on my figure. So it says angle subtended by a chord at any point on the circumference, angle subtended by a chord at any point on the circumference, is our circumference. So what we are going to do next is we are going to draw a chord. So let me name this point as B. We are going to use this point again. So from this B point we are going to draw a line. We can draw it at any point of the circumference. Right now I am drawing it at T2. According to our property, angle subtended by a chord at any point on the circumference, we have drawn our chord B2, and this is going to be the angle subtended by it is equal to the angle between chord and the tangent. We have another chord BT1, and the angle made by with the tangent is del. So this angle is going to be equal with this angle. So both of this angle are going to be equal. So that's what our third property says, or simply we can use our second property in this as well. So what our second property says that angle subtended by any chord at the center is equal to twice the angle between chord and tangent. So this is going to be 2 del. So this angle is going to be simply half of this angle from our property 2. So this is simply going to be equal to del. So we can so from our third point we can write this as angle IT1B equals to angle T1T2B. So angle subtended by a chord at any point on the circumference, which is our angle T1T2B is equal to angle between chord and tangent, which is our angle IT1B. Now we move forward to our fourth property. In our fourth property we'll be calculating our length of back tangent, which is simply equal to our length of forward tangent. As we already talked before about this, both the backward and forward tangent length are equal, and this length is simply equal to r tan del by 2, r tan del by 2. So let me show how. So as you can see over here, we have our radius r. So right now we need our length T1I or IT2. So if this whole angle is equal to del, this angle is going to be equal to del by 2. So if we use tan del by 2 equals to perpendicular, which is our T1I, over our base is equal to OT1, which is equal to r. So therefore our forward or backward length are simply equal to each other, which is equal to r tan del by 2. So this is how our formula is derived over here. Next we'll find our length of our curve. So what is our length of the curve? So we need to find our length of this curve. From T1 to T2 we need to find our length of the curve. So what we have for our length of the curve is our 2 pi r equals to 360 degrees. So we have our that relation for our circle. The overall circumference 2 pi r will be equal to 360 degree. So 1 will be equal to 360 degrees. So 1 degree will be equal to 2 pi r by 360 degree. So right now in our case the angle subtended is del. So our del will be equal to 2 pi r del by 360 degree. So as you can simply see, we have used our simple unitary method. So our length of the curve will be simply equal to 2 pi r del divided by 360 degree, and our del must be in degree, so our length is simply equal to pi r del by 180 degree. So in our number 6 we have our length of long chord, length of long chord, and our length of long chord, so let me write it down over here. Our length of long chord is simply equal to 2r sine del by 2. So let me show how this is equal to 2r sine del by 2. So as I explained before, our long chord is from t1 to t2. So right now again we'll be using our right now will be, so as you can see here, these two lines are perpendicular to each other. So right now t1 2 we have used our we have divided in half. Our del is this much angle is equal to del by 2. So right now we'll be using this triangle OT1, and this you can name this as, let's say, A. So on using this triangle, what you simply get is what you're going to get is sine del by 2 equals to perpendicular by hypotenuse. Our perpendicular is AT1 divided by hypotenuse is A. So our AT1 will be equal to R sine del by 2. So our AT1, which is equal to AT2. Our overall long chord is running from T1 to T2. So simply multiply it by 2 in order to get our AT1 is R sine del by 2. So our overall will be simply equal to 2 times 2R sine del by 2. So this is our length of long chord is derived. So in number 7 we have our mid ordinate. We are going to find our length of mid ordinate, and our length of mid ordinate is going to be equal to so let me show from the figure only. So our mid ordinate, as I explained before, is this much length from our midpoint of our long chord to our midpoint of our curve. So this length is our mid ordinate. So in order to find our mid ordinate, what we simply need to do is we need to subtract some distances. We have this overall distance as r, and if we subtract this small distance, this much distance from our overall r, we are going to get our length of mid ordinate. And so if we simply use again our cosine component in this time, so in this case if we use our cosine component, cos del by 2 will be simply equal to, for this case right now previously we used our sine component. On using our cosine component, our cos del by 2 is equal to our base. Our base is OA. So this length is equal to OA will be equal to r cos del by 2. So let me show from here our overall this length from here to here, our overall top length from O to the top of our curve is our r, and our OA is OA will be equal to r cos del by 2. So if we subtract this, so if we subtract r from r cos by del by 2, the remaining will be our length of our mid ordinate. This is our r, this is r cos del by 2. So if you subtract r from r, if you subtract r and r cos del by 2, the remaining length is going to be is your length of mid ordinate. So in our number 8, so after mid ordinate we have our apex distance. So our apex distance, so let me show you what is our apex distance. Our apex distance will be simply equal to, so now for our apex distance is simply equal to this length. So this was our mid ordinate, this is our long chord. So this distance, so let me name this as B. The distance from B to I is our apex distance, and our apex distance will be simply our difference of r sec del by 2 minus r, and this is simply equal to r, if you take r common, sec del by 2 minus r minus 1. Sorry. So what we are going to simply do is for this triangle we are going to take our sec component, sec del by 2, which will be overall equal to our OI. Our OI will be simply equal to r sec del by 2. You can use the same formula as for sine and cos, and if you subtract r from this r sec by 2, this is our r, this is our overall r sec del by 2. If you subtract r, we are going to get the remaining distance bi, which is equal to r sec del by 2 minus 1, which is our apex distance. Now for our final 2 points, we are going to find our chainage of point of commencement, and in number 10 we are going to find our chainage of point of tendency. So after doing this, after these two properties, our overall properties of our relations between different elements of our simple circular curve is going to end. So as I explained before already, this is our point of commencement, is our point T1. This is our point T1, and this is our chain. We need to find the chains of this point, and in order to find chains of this point, what we're simply going to do is, from our chains of point of intersection, we are simply going to reduce our length of back tangent. So our length of back tangent is T1I. We're going to have our chains of point of intersection. So let's say we have a certain point over here. From this point up to here, we are going to have our chains of point of intersection. We are going to have the certain tangent. We are going to have the certain chains. From this certain chains, we are going to subtract this T1I, which is our length of back tangent. On subtracting this, we are going to get our chains of point of intersection. So, on subtracting our back tangent from our back tangent from our chains of point of intersection, we are simply going to get our chains of point of commencement. So our chains of point of commencement T1 will be simply equal to chains of point of intersection minus length of back tangent. So knowing our length of back tangent and our chains of point of intersection, we can simply find our chains of point of commencement. So now in a final, we have our chains of point of tangency T2. So we need to find our chains of point of tangency T2. So as you can see over here, in order to find a tangent of chains of point of tangency, what we are going to do is, we are going to have our chains of point of commencement, and for our chains of point of commencement, we are simply going to add our length of this curve. We are going to simply add our length of the curve. So our chains of point of tangency T2 will be simply equal to our chains of point of intersection plus our length of curve. So as you can see over here, we have a certain difference from our chains of point of commencement and chains of point of tangency. So you might have a question that why didn't we add our forward tangent in order to find our chains of point of commencement? This is because while we are moving from T1 to I and from I from T2, our direction of alignment is not this. We do not follow this direction of alignment, but we are going to follow our alignment of the curve. From our point I1, we are going to move forward using forward in the sense of our curve, not following this forward tangent. Such forward tangent doesn't exist in real life, because instead of this forward tangent, we have introduced our curve. So our chains of point of commencement, chains of point of tangency T2 will not be equal to our forward tangent, but it will be equal to our length of the curve, because it depends because of the alignment or because of the direction which we have followed. Because as you can see here, from T1 to I, we'll be following our forward tangent, we'll be following our alignment, but once we reach our point I, so let me show my direction of alignment. So this is my first direction of alignment. So I can so right now I can subtract my backward tangent in order to get my chains of point of commencement, but for my chains of point of tangency, I am going to use this direction of alignment. This direction of alignment will be followed. So we need to add our length of the curve. So that's why we cannot use our forward tangent. Hope you have understood why we have added length of curve over here, and why we have added length of back tangent over here. Next we'll be solving our numerical relating to different relations in order to get the concept even more clearer. So now we have a question over here. So we'll be solving this question using all those formulas which we using all these formulas which we have talked about before. We'll be using this formula, all this formula, to solve this question so that our concept even gets more clear. So right now what we have in our question is, two straights intersect at a chains of 2056.44 meter and angle of intersection is 120 degree. If the radius of simple curve to be introduced is 600 meter, find the following: tangent distance, chains of point of commencement, chains of point of tangency, and length of long chord. So we haven't been given any figure over here, so let me firstly draw the figure. So our figure will look like this. So firstly we are going to draw a simple circular curve. So I'm going to draw the figure roughly. So let me draw a simple circular curve in this way, and we are going to have our first back tangent over here, and it's going to be our forward tangent. So let me draw my radius as well. So let me draw my long chord. So my long chord, my point T1, point T2, and we have so let me just draw. So let's say this is my center O, and we have our radius in this way. So as mentioned in my question, what is the angle of intersection? This is my angle I. So as I mentioned before, this is going to be angle of intersection. So let me draw this line a little bit forward. So my angle of intersection is equal to 120 degrees. So this is going to be my angle of intersection. So and my radius is 600 meters. So this both distance are 600 meters. And next what I have been given is the chain is of intersect at a chain is of 2056.44. So the chain is of intersection. So the chain is of intersection is going to be equal to 2056 point. So the chain is of this point I is 2056.44 meter. So let me write it down over here. So let me write this over here. Firstly, the chain is of point of intersection. So our chain is of point of intersection is going to be equal to 2056.44 meter, 2056.44 meter. And next what we have is our angle of intersection is 120 degree. So I'm not going to write that, so just write other angle. So angle of deflection, we haven't been given our angle of deflection. Our angle of deflection is del. So this, as I explained in the property before, these two angles are going to be equal. So according to our property 1, so as I said, in property 1, our angle T1 or T2 will be equal to our angle of deflection. But right now we haven't given any angle of deflection, and our angle of deflection will be simply equal to 180 degree minus 120 degree, using our simple linear property. 120 is equal to 60 degree. So this will be 60 degree and this will be 60 degree as well. Now we have our radius as well. We have been given our radius 600 meter. So firstly we need to find out tangent distance. So our tangent distances, which is our IT1 or IT2, whatever you say, both are equal, IT1 or IT2. So as I already derived my my formula before, my length of forward and backward tangent is equal to R tan alpha R tan del by 2. So using that, I have my R of 600 into tan, I have my 60 degree divided by 2. This will give me a result of 346.41 meter. So my first question is done. Next I need to find my chain of point of commencement and chain of point of tendency. So I can find my chain of point of commencement easily. So I have my chain of point of commencement, So as I already talked before, my chain of point of commencement is going to be equal to be chain of point of intersection minus backward tangent. So chain of point of intersection is given as 2056.44 meter minus my backward tangent IT1 is equal to 346.41 meter. So as I explained before, my chain of point of commencement will be simply equal to 1710.03 meter. So next, in my third number, I need to find my chain of point of tendency. So as I explained before, in order to find my chain of point of tendency, since we will be following this alignment for our tendency, I have my chain of point of intersection, which is 2056.44. Next I need to add my length of curve in order to find my chain of point of tendency, 22. So let me find out my length of curve. So let me put it over here, length of curve. So as I explained before, my length of curve is given by formula pi r del by 180 degree. So I have my pi, I have my r 600, I have my del 60 divided by 180. You need to make sure your del is in degree, since we have 180 degree, and we are going to get our length of curve as 628.32 meter. So simply we have our length of curve as 628.32 meter. So on adding these two, I am going to get my chain of point of tendency as 2338.35 meter. So finally it is asking my length of long chord. So length of long chord. So my length of long chord is simply my distance from T1 to T2, and my length of long chord is given by my formula 2r sine del by 2. So let me simply put on the formula 2r sine del by 2. I have my r of 600 meter, I have my sine, and my del is 60 degree divided by 2 sine 30 degree, and I am going to get this as 600 meter. So in this way I have given a basic introduction to chords. So if you like our video, do subscribe the channel, and if you have any queries, do comment down below. And if you want to see more of my more of such content, and if you like my work, do subscribe to the channel. Thank you.